So hi everybody, thanks for coming. Anybody excited for lunch yet? Not too many, great. So we have plenty of time to pay attention to my talk, yay. So I'm very excited about C++ 17 and I hope many of you guys are as well. C++ 17 brings a lot of things to the table, but if you're anything like me, you get to know about these things at conferences, at YouTube videos, or from standard proposal papers. And you read about these things and think, hey, this is really cool. I would really like to use this in my code. And then you can't because you don't have a compiler available that actually supports these features quite yet. So I've been working on a new commercial product called Clang from the Future that hopefully can help you a little bit in that situation. But I'm getting ahead of myself. Let me introduce myself really quickly first. I'm a Berlin-based consultant, and I work on helping your company do things more efficiently, basically. So maybe you've tried code reviews, for example, before and found, yeah, code reviews are really great and stuff, but we spend a lot of time on them, we don't really get a lot of stuff done, and ultimately they don't pay off as much as I would like to. So I can help you figure out why that is and how to do things better. Similarly, if you find a lot of regressions in your code and need better continuous integration infrastructure, or better testing, that's something I can give advice on as well. I'm also doing a little bit of contracting. My main focus here is the symbiosis between low-level domains, like embedded systems, operating systems, or simulation software, with the zero overhead abstractions that C++ allows us to implement. I've got a couple of open source side projects. That's usually a console emulation software where most prominently I worked on the Nintendo GameCube and Nintendo Wii emulator software at Orphan. So if you want to learn anything about computer architecture, these are really, really exciting projects to look into, both from what they can do and from the technical perspective as well. So I can really recommend checking those out. And yeah, there's a couple of social media links if you want to learn more. But yeah, why are we actually here today? Why is C++ 14 and why is C++ 17 such a big deal? And a lot of other people have given talks on this, so I don't want to summarize all of the features, but just a quick reminder. There's roughly 4 categories of things. The first one I have is mostly syntax sugar. So small things that we could have expressed just as well with C++ 11, but which are just ever so slightly better to implement nowadays. So the first example here is the so-called structured bindings, which allow you to take a tuple or a pair and conveniently destructure it into multiple different variables. The advantage being you don't need to access the return tuple through the .first and .second members anymore. Another new thing is the binary literals. You see the 0b prefix here, and the digit separators right here, which just allow us, especially if you're working on like embedded systems where you often need to set specific CPU flags or register flags, you often end up with these magic constants that, like 130, for instance. So it's just this bit set and this bit set. And from the constant 130, you might not evidently see where that's coming from. With such a binary literal, it's just painfully obvious. That can really make code reviews, for instance, more effective, because in code reviews, I've often had the instance where I've written such code without binary literals and without digit separators. And I was just like, yeah, this is obviously like this bit and this bit. Just that I forgot a 0 at some point and ended up with the wrong constant, and it just slipped through code review as well because, well, without these things, it's just not all that obvious that it's wrong. And the final one is the if-init syntax that allows you to create a variable and then check for validity all in a single if condition body. That can be beneficial if you really just use this variable in the if body and don't want to leak it outside of the if body. So that's syntax sugar. Another thing is standard library additions that allow us to construct more type-safe code. So we might have a parser that either successfully parses a token or doesn't. And in the doesn't case, it usually would return some sort of null pointer constant or a Boolean flag indicating success maybe. So that's kind of suboptimal because then I always need to remember that you need to check for success and need to access the actual result indirectly, so it's kind of annoying. And optional really is a nice abstraction to handle both of these cases and reliably remind people at the core side, hey, this thing might fail. Similarly, state variant is kind of type-safe union. It's just a very concise example, but there have been talks at this conference as well that go into more detail about it. So standard library additions for type safety. And then the bottom left is similar in spirit to the syntax sugar category, although I would like to draw a distinction here because it doesn't only just write things more concisely and more neatly, but it actually allows us to write very powerful constructions in extremely concise manners that would have been infeasible to write out manually before. So the prime example here is fold expressions, where you can have a variadic template of bars, and each of these bars might have a member function called foo. And for whatever reason you want to sum up all of these results of foo, might be integers, and return the final result from the function. If you think about how you do that pre-C++11, with C++11 you might do it with a variadic template and parameter pack expansions, but it usually ends up with recursive template solutions, and these are kind of ugly, especially if you want nice debug builds. So in a debug build you would have a symbol for each of these functions, and where you step through a debugger you would just end up going through the stack frame like that. Whereas with fold expressions you just get one function that does precisely what you'd want. Right, and the other one is ifconst_expr. I guess we all know that since Andre's keynote. Contrary to what he was saying, I think it does serve some valid purposes, even if it's not as powerful as we'd all like it to be. But yeah, so this is not a particularly convincing example, but in my personal code I use it for quite a lot of neat things, so that's quite nice. And then the fourth category is actual new features, and there aren't a lot of them actually in C++14 and 17. But a couple of them. The most important one is the std file system library, which now allows you to, in a standardized way, access paths and do file operations. So that's quite nice. Small disclaimer ahead, my tool clang from the future doesn't take care of this quadrant. It only takes care of the top left, top right, and the bottom left one, because just re-implementing std file system would be a little bit too much work to be feasible. Plus there are other solutions available, like boost file system, for instance, if you're really curious. Right, and there's also, for more information, you can just Google the C++17 Tony tables for more examples. Right, so we've got a problem. We've got a nice C++17 program making use of, so in this case, just a very simple example, binary literals and digit separators. And we've got a very proud programmer who says, hey, we've had this very bad way of writing hard-coded constants, and now we've got this beautiful way that clearly expresses why this constant is 128, because I want to set this specific bit. And also the digit separator is nice because, you know, previously you might have a bit of trouble counting the number of zeros in that constant, whereas now you can easily see, hey, right side is 4 zeros, left side is 3 zeros. So you know the 1 is at the 8th position, so it's 128. And compile that with GCC 4.8, and you get a binary program out that sets first CPU register to 128. Just as expected, you get a happy face programmer. That's great. Now, retarget the same application to a different platform, using GCC 4.8, for instance, because it's somewhat more legacy, perhaps. You don't get an assembly output because you have to realize GCC 4.8 doesn't support digit separators. That's really annoying, because we found this really nice way of expressing our ideas. It's just not supported by our compiler. Makes for a very angry developer. So what can we do about this? There's two classical solutions that probably everybody's aware of. Either you update your compiler. That's great. If you can do that, go ahead, do it. You don't need my tool, really. But that's not always possible. There are some legitimate reasons why you might not be able to update your compiler. The most important one being, well, maybe there is not any more up-to-date toolchain for your platform. Especially embedded systems suffer from that a lot, so you just simply don't have that option. Similarly, some people have weird dependency chains, so to speak. Their compiler might, through that dependency chain, be tied to their operating system version. So updating their toolchain might be equivalent to updating the operating system, and that can be a very invasive change. So there's a balance to strike between the effort of updating and the actual functionality that it yields us here. The alternative is stick with old C++, and deal with the consequences of that. And it might not sound all that bad. We've managed without C++17 for the past few years just fine for the most part anyway. But it's just an unused potential right here. Think about like how much time does it need you to update your compiler eventually? So maybe 3 years from now, 5 years from now, a new update for your toolchain will be released and you will be updating. Cool. So how much code will you be writing in those 5-year time span? How much code, in other words, how much code in 5 years from now will be based on outdated technology? And how much effort will it take you to bring that old code up to date with the modern standards? So now I'm presenting a new solution for that, which is called Clang from the Future. And the idea is basically you take your old toolchain, you keep using it just fine, but you teach how C++17 works. So yeah, this is a libclang-based tool, more on that in a second. And the idea is it's not a replacement for your compiler, it's a preprocessor step that is run before your actual compiler. And if you look at the regular compile pipeline, you get the regular source code on the very left, it runs through the C++ compiler, through the linker, and then gets you an executable. So CFDF gets inserted at this stage and inserts 2 additional pipeline steps. The first one being is that you build an abstract syntax tree representation of your program. This is what libclang is doing for us. And then it converts that AST by using some intelligent pattern matching to equivalent C++11 source code. So that's quite nice. The idea is all of this is automatic, so you don't need to inspect the output of the C++11 source. And it's just fed directly to your actual compiler. In other words, okay, fair enough, that's on a later slide. So let me just make this very clear here. Keep using your front-end compiler. You don't need to change anything about that. And it's really just this CFDF build step in front of that. As a black box, you don't need to inspect the output. It takes care of transforming this getMask function to getMask function, which just directly uses 128. So the advantage is you can keep using those C++17 features, but they will still work on an old compiler that doesn't understand them. So if you look at the problem case we had before, we now have the C++17 code, run CFDF on it, get the C++11 compatible program out, and can just use GCC 4.8 and get a happy face program out of that again. Right. By the way, if you've got any questions, feel free to interrupt me at any point. I don't mind, and I appreciate the more interactive session compared to a lot of questions at the end. Right there?
So basically you're doing some sort of source translation.
Yeah, it's a source-to-source transformation indeed.
That it's actually show the right line, or yeah, does it include some problems on what we expect to see and what we actually see there?
So the question was, how do we debug programs that were output by CFDF, basically, isn't it? Yeah. Currently, you don't. That's one major issue with the tool, actually, right now. I was hoping that question might come up somewhat later and not right in the front, but well. I've got some ideas on how to tackle that problem. So technically, it should be feasible to read the compiler, like the front-end compiler output executable, and read in all the draft symbols that describe the debug information, and decode that, and patch up all the line and source information in there. That's an idea I have, and I think it's doable, but it's far from the priority list right now. But if potentially I have a customer that's really, really interested in that, it certainly can be prioritized, for instance. So yeah, good question there. Right, how does it actually work? Let's see, so as I was saying, it's a libclang-based tool. Libclang, for those of you who don't know, is basically Clang turned into a library. So it takes care of all the nasty parts about C++ with us. It does all the tokenizing, it parses the language, and this provides this very convenient abstract syntax tree for us that we can work on. There's a lot of tools that use this library. Just here's a small excerpt, and I apologize in advance if I found any well-known tool here that should have been listed. But yeah, just to give some examples, ClangTidy might be the best well-known. It's like a massive toolbox of various refactoring solutions that you might apply in your code base. C++ Insights is also a very interesting project because it's conceptually similar to what I'm doing, but more targeted towards educational purposes, where you want to teach people who are used to C++ 03 how C++ 11's abstractions work. So for instance, a range-based for loop might be destructured into a plain iterator-based loop. And the tool does that automatically, and you can look at the output and see, hey, okay, so that's how this abstraction works. My tool goes in a little bit of different direction because it's all automated and the output is not targeted towards human readability, but rather about enabling C++ 11 compilers to compile the C++ 17 source code. Whereas in this case, sometimes you might not be quite so accurate to the semantics, just so it's more readable and gets the idea across. And yeah, there are a couple of reflection frameworks. Arvid Gerstmann has actually presented one of these that was libclang based at this conference, I believe on Thursday. So definitely check that out if you're interested. And there are a couple of static analysis tools and just a vast majority of tons and tons of custom tools that are used internally by various companies to achieve company-specific goals. So what does it look like? If you look at this function, libclang provides us with this abstract syntax tree, and you probably have seen one of these before. Right, so you've seen one of these before, I hope. But just in this particular example, it looks like this. You've got a top-level node, which is the function declaration. It's got 3 subnodes, one being the actual return type, one being the list of function parameters, which in this case is just empty, and one being the function body, which in this case is just a single statement, but it could also be a compound statement, for instance, which then has various statements as children again. And yeah, our actual integer literal ends up as a child node of this return statement. So that's kind of the structure of what we get from libclang. And as you might imagine, this is already quite convenient because we didn't need to pass anything. It's just send it all for us. But libclang is actually even better than that. It allows us to, so we don't need to work on this entire tree on our own and like do tree traversal ourselves, but it's also abstracted away from us. So Clang has this concept of AST visitors, where we can call a user-defined C++ function for each kind of different node. So this is just the same tree as before again, but now you can see that for the function declaration, we might call a user-defined function called visit function decl. The return statement gets a visitor for visit return statement, and similarly integer literals and the parameter lists. So that's really powerful, especially because it's all defined by a class called recursive AST visitor. So in other words, if we only really care about the return statement, for instance, we don't need to define all the other visitors. We just define the visit return statement function, and that's all we have to do. And in our case, that means we want to specialize this visit integer literal function. Well, let's see how that looks like. So we define a subclass of the recursive AST visitor called myASTVisitor. And it takes the Clang integer literal, which is a Clang-specific class, and we can work with that. We can just ask the literal, what is your value, independently of how it's represented in the source. If it's using a hex, that's a hex literal, it just returns the value. If it is a decimal literal, it just returns the value, and the digit separators don't really factor in at all. And when we get that, we can just say we have a kind of rewriter that modifies the source code in place. And we replace the original source range of the literal with the plain decimal version of the literal value. And that's really all there is to it. So we get this function, we convert it to the plain decimal, and we're done. So that's one C++ 14 feature, 2 14 features actually, that we just solve with 2 lines of code. I was massively impressed by how easy that was, actually. I was kind of drunk by how easy that was, actually, and I was like, cool, now let's do something really complicated. Let's do const xpref. And boy, was I naive about that. So let's see. We've got a function here called makeSound. It's a template. It can either take a cat or a dog. And it wants that animal to make its respective sound. So a cat might meow, and a dog might woof. And obviously, a cat cannot woof, and a dog cannot meow. So we use if const xpref so that we check for the type of the cat, for the type of the animal. If it's a cat, we meow, otherwise we woof. And if const xpref makes sure that the branch that is not taken in this case will always be crossed out, because otherwise the code wouldn't compile. And libclang supports that kind of stuff. So we can, again, just get a abstract syntax tree representation of this. And this time we get a function template decl, which has a single parameter and an if statement as its body. And the if statement conversely got this really ugly condition expression. It's got a function call expression and another function call expression for the if and else branch, respectively. And what we want to do in this case here is we want to customize a function visit if statement that then modifies this if statement so that the wrong branch is crossed out. But here's the problem. Which branch is it actually? Which is the branch that we want to cross out? Because we can't statically decide that. Because if the user uses make sound with cats, well, we want to cross out woofs, obviously. But it might use both. And what do we do in this case? It's not obvious. And they're like really ugly C++11 hacks, but I'd rather not go there. So I've been thinking about what does a proper compiler do in this case? And a proper compiler in this case does nothing with this template. It waits until the template is actually used with a cat or a dog. It's used for a cat. It goes ahead and creates an implicit specialization of this template for cats specifically. And then, in that case, once you're in the specialization, you know, okay, cool, so it's a cat, so no, the cat is supposed to meow, and the other thing is just not going to happen. So I've been going ahead and feel like, okay, if that's what a proper C++ compiler is doing, maybe that's what Clang from the future should be doing as well. So what we do is we take this function and we explicitly specialize it for cats. And since we now know that it's a cat, well, we can statically decide which branch is taken and just replace this woofing with a nothing. So that's already a win, and we just do the same for the dog. And it solves our problem. So that's right. And also, so one design philosophy in Clang from the future is that I try not to do too many weird replacements in your code. So you might expect that I replaced all of the t's in the template with the actual type, but instead I actually just re-export the template parameter for the actual concrete type in the template. So I don't have to modify the body itself too much. It just keeps working. So this is a component I call the template specializer for obvious reasons. It's like pretty much the biggest component in Clang from the future right now. It's like pretty much 40% of the entire code base, excluding tests. So it's quite a complicated problem, much more complicated than I make it look right here. But yeah, it works just fine, and it allows us to do all these kinds of transformations that otherwise might not have been statically decidable. That's cool. If we look at the if we look at the abstract syntax tree here, we wanted to implement this visit if statement function. That's what I'll be doing here. First thing we want to do is check, is it a const expr if? Because if not, well, we have nothing to do here. If it is, we keep going. And we ask, what is the conditional expression used for this if const expr expression? And Clang allows us to query what is the static result of that conditional expression, gets us the result, and then based on the result we can pick the then branch or the else branch, which is the branch that we keep around. And that's all we need to know. Then we can start rewriting things. And so the first thing I do is remove the const expr by just replacing the if const expr bit by just plain if. And then I replace the actual branch bodies by just nothing. So this looks rather complicated. Don't worry about the details too much. But you can see there's a branch depending on whether the expression was true or false, and we rewrite different things. So hopefully you believe me, this is doing the right thing. Right. So we could keep playing this game now and could show you different C++17 features and just exercise how it looks like in the code. How does one actually use the tool in practice? Well, it's very easy, actually. You just use it like any other compiler. You call it CFDF. It's a command line-based tool, and give it the input source file. And then you also specify the front-end compiler that is supposed to consume the C++11 output. And that works, but obviously we rarely actually type manual compile commands anymore these days. So instead we use a build system, and that's why I've been putting a lot of effort into making sure that this thing integrates as cleanly as possible into your existing build pipeline. If you're using make and follow common standards, you can just override the CXX environment variable to point it at a different compiler, CFDF, and then you add the front-end compiler CXX flag to the command line, and then just call make. That will work. If you're using CMake, it's even better, because the command line gets somewhat more complicated, but CMake keeps these settings around. So once CMake's running and the configuring process is done, you just call make, you call Ninja, whatever front end you're using, And it remembers those settings and it just works. And like once you're past the CMake step, you basically don't even notice that CFDF was running anymore. Other setups may need some creativity. That's just an artifact of the early stage of the tool right now. But depending on your needs here, that's certainly something that can be prioritized. But yeah, there's no Visual Studio integration right now, no Xcode integration, for instance. But if you're using GCC or Clang on Linux or any derivatives, it will just work. Right, showcase. So this is the part where I show you a couple of things in action. Let's see how we do this. Yeah, that should be fine. Not that one. There we go. So the first example that I meant to show was the if init syntax. So you might know that std_map has a function called inplace, which yeah, the color scheme is unfortunately not too great, but is it roughly readable in the last row? Can I get a hands up? Any better? Okay, getting thumbs up there. Cool. So this inplace function doesn't return like a Boolean or anything. It returns a pair of an iterator to the inserted element and a Boolean indicating whether the element was already there or not. So if I use a key 5 here, the element with a key 5 might have already existed, in which case the Boolean would be true. So yeah, we do this. We initialize this variable, which is a pair, and then check it.status.second. So it kind of breaks on that line, but right here it says it and status dot. Is it just called con? Well, whatever. So it's accessing that tuple member anyway. Yeah, there it is, second. In that case, it says added, because it added a new element. Otherwise, it does not. Right, so let's check this. CFDF minus front-end compiler equals, let's use GCC on 00 if init. We can just pass any command line arguments that GCC would understand in here, like O_test or minus O2, O3, whatever. Output some stuff, and here you see a temporary file was created with the C++11 source code, and it calls G++ on it. If we call ls now, we see there is this test executable. Run that, and it just says what we'd expect it to say. So that's great. Now, sometimes it can be usable to actually look at what the tool output, and I'm sure you're kind of curious what actually happened behind the scenes here. So I wrote a small tool, well, not a tool, a script, that just runs Clang format on the output, so it's a little bit more readable, and then runs nano on that. Right. So what I can do is I can just run CFDF and replace the front-end compiler by another front-end compiler, namely edit.sh. So that will just compile the thing and wait for an input and then open the output in an editor. So we can see here now, the if statement has just been swapped out with a regular if statement that just has a regular expression as a condition. But the variable declaration has been moved outside of that, so a C++11 compiler can understand it. But notice the attention to detail here, because it also introduced a new scope using curly braces here, which is necessary to make sure that the variable doesn't leak outside of the scope of the if statement. Right. So that's that. Another example is just the same we've seen before, which is the make sound example. Just wanted to show that one in practice as well. By the way, to save some time, I will not compile these specifically now. Just trust my word, maybe, that all of these do compile. And just look at the output. So as we see, we first have this. What used to be the definition is now just a forward declaration of the template. and the actual explicit instantiation are explicitly marked using specialization generated by CFDF. And then we get a template specialization for struct cat with some annotation of the contents that were replaced. Struct cat in this case, re-exporting the template parameter, and as you can see, the else branch is gone. And similarly, we get the same for the dog, and that just works. Somewhat more non-trivial example is the next one, where I decided that a meowing cat returns an integer, because that makes sense. And the woofing dog will return a string, because that also makes sense. And our makesout function now is in that dilemma: which type should it actually return? Should it return the integer or the string? So what I'm using here is the auto return type in C++14, which decides, okay, depending on what we actually return in the function, I'm adapting my return type. If you think about how you'd write that in C++11, it's not actually all that easy, because, well, you'd have to forward declare the template and then explicitly specialize it, but once you forward declare it, you have to give a return type. You can't auto forward declare a thing, especially not in C++11. So let's see what clang from the future is doing here. Whoops, sorry, that is the next example. Whoops, what am I doing? So you can see it's a lot of code. Let's look at the actual template declaration. You can see the auto was replaced by the CFDF deduced return type makesout of t : type thing. Okay, what is that actually? Well, we just forward declare it here. Okay, well, let's just keep going, I guess. We look at the first specialization and we see, okay, that's where we specialize this return type for cat. And for cat, we say the return type is an integer. Cool, so that's what it is. Then we explicitly specialize the template again, just like before, but notice that it automatically filled in the auto return type with the concrete return type int. And similarly, for the dog specialization, we again specialize the return type, and then, oh yeah, by the way, this is kind of, this is just a stat string, but it's Clang's weird way of saying, yeah, this is a stat string. But yeah, it works. So the formatting is kind of wonky here, apparently. But other than that, it just works. So that's cool. And that's certainly something that would have been really, really annoying to write out by hand. And it's great that the tool can just automatically take care of this for you. Right, next example, structured bindings. We've seen this one before on the first slide as well. So we just have a function, my fancy function, returning a string and an integer. And instead of working on the tuple directly or on the pair directly, we just want to save this in two separate variables, string and number. So let's see how CFDF addresses that. So what we do is we create a temporary variable with the contents. CFDF binding group is what I call it, string and number. And then through some convoluted ADL lookup logic, it's great, we extract the actual tuple members using std_get, the first index and std_get of the second index. So we get our string and number and can just use those variables in the output stream. So that's nice. I won't show the next two examples. We'll just show the code. It also works for user-defined structures, where you can destructure a plain or data structure. And it also works for user-defined data structures with manually customized std_get functions. But there's no new insight in here, so I'll just skip those. What's more interesting is fault expressions. So I've written this little function called sum, which just sums up all of its arguments and returns the result. So if you think about how you'd write that function, you'd probably use a for loop or something, but there might be valid reasons why you want to do it like that. And you can see it's like a really concise way of writing things down. So the arguments I'm using here is just 1, 2, 3, 4, 5. The result is 15. And I'm achieving that just by using this ts plus ... plus 0 expression. That's like super compact and great. You can use that for lots of stuff. So let's see what CFDFs are doing for this one. That's the wrong one. Right. So we've got 3 core sites. That means 3 combinations of template parameters. And it just generates explicit instantiation for each of them. The single parameter case is boring. Let's skip that one. But the one with 5 parameters is just, in a sense, very beautiful because it just replaces the parameter pack with the explicitly written out 5 groups of types. It expands the parameter list and expands the actual usage side. There's a small bug that it creates a redundant plus right here currently, but doesn't change the semantics in this case, so that's great. And it also takes care of the empty case just fine, where it's just 0. So it's a really cool feature and it just works. I've got brought a little something with me. This little bad boy. This is an ESP32 chip, which is quite popular in Internet of Things applications. And the vendor for that tool has the custom toolchain like many embedded systems. And in this case, the compiler that I installed is just like extensor ESP32 ELF G++. You can try compiling this example using that compiler. And you will notice, well, okay, this won't work either way because I didn't specify a standard. But if I try to compile using C++1Z, which is the best it supports, you can see, yeah, that compiler doesn't support quote expressions. But well, that's why I wrote the still editor, isn't it? So I can just say CFDF with the front-end compiler, extensor blah G++, and the same parameters out there. And this would fail linking because runtime libraries for the thing and stuff, so I'm just compiling it. But it just works. It says invoking that thing, and it also outputs the std out for that compiler, and it's empty, so that means everything was fine. If we see, there's the .object file, and I can run that through in disassembler, which I never tried, but okay, my disassembler doesn't support that platform, but I can run it through object dump. Hello. Well, this is what you get for improvising, I guess. Okay, just believe me, it's a valid object file. I mean, you've seen it doesn't output anything, so it should be fine. Great. So that's all the examples I wanted to show. There's like also one example for parameter pack expansions. Those are also supported and can technically be transpiled back to C++03, which is quite nice, I think. But yeah, to save some time. What the tool can also do is the CMake integration, and for that I wanted to show off the. Well, I wanted to show that off in action as well. So if you just use the command line provided in the slides. You can see it just runs through just fine. It says detected working CXX compiler, and it creates build files, which I can just run. It outputs a lot of stuff. But you can see it just works and builds my target for the test suite of the tool. So that's just great. And that's precisely the kind of easy and transparent integration that I was hoping to achieve, because you just run a somewhat complicated initial setup line, but then it just works like regular. Just call make and it's done. Right. Just wondering, how am I doing on time? Okay, that's good. Right, so that concludes the showcase. And now just some general notes again. Current status. What can I do? Well, what you've seen today, or in the past 10 to 20 minutes or so, is pretty much all that's currently supported. So I'm focusing on really getting a core set of C++14 and 17 features working as stable as possible. Because I think, yeah, it certainly would make for a great selling point if the tool supported all of C++14 and all of C++17. But it's a rather useless tool if you run it on your code base and what comes out is just garbage. Nothing runs anymore after I failed. So I'm trying to make sure that the set of features that is supported works, and works great. Similarly, I want to make this a really usable drop-in plugin. I want to make the integration as painless as possible for you. That also means that I really haven't been able to spend the effort on Windows and macOS support right now. macros probably works if you like compile through the command line, but if you're expecting Xcode integration, as I've been saying before, it's not going to work yet. But certainly it's planned for the future. Yeah, small initial set of features, correctness first line features. It's available for licensing right now, especially because if you are interested in this product and want to participate in the design and prioritization of features, that's the best way to get into it right now. There is a open source prototype available on GitHub. You can check that out, but it's really early stage kind of thing and really mostly for educational purposes. If you're interested in writing libclang plugins or in the general idea, that's something to look at, but I won't be planning on updating it for another while. That said, I've got some ideas on how I can make it easier for developers to try out the tool. Not something I can talk about right now, but it's certainly something I'm hoping to be able to talk about later in a couple of months. So look forward to that. But yeah, full version is proprietary. Future. More rewriting rules. I do want to expand on the set of supported features. Fold expressions is nice, fold expression is great, and especially that I'm able to use fold expression on my ESP32 is awesome. But there's more to do. And once we're done with that, we can look beyond C++17. Can we actually go all the way up to C++20? And there are some really, really exciting features to be had here. There's contracts, there's concepts, a couple of others, obviously. But like these two in particular are reasonably easy to transpile. And I'm really hopeful that, like, if you're not too excited about C++17, maybe this will be the convincing argument right here. Similarly, we don't really need to stop at C++11. So I was thinking, yeah, probably what people care about most is C++17 or transpiling C++11 back to C++03. I was genuinely scared of doing that. And the reason I was scared about it was move semantics. Like, move semantics are just plain horrible, is what I was thinking anyway. Actually, last weekend, something occurred to me, and I've now got a rough idea of how I think it might be possible to transpile move semantics. And that might actually enable my tool to transpile all the way back to C++03 and 98. So if that was another reason you weren't excited about it, maybe that changes your mind as well. But a test coverage. I want to take as many cutting-edge C++17 applications as I can and test out the tool with it. Whether I'm successful at actually transpiling them back to C++11 is an open question, but at least making sure that all the transformation I'm doing right now don't break anything is a major goal of the tool right now. Robustness against macros. Technically, this isn't much of an issue. Because worst case, I just expand all the macros that affect rewriting rules. That's okay. That works. You're not supposed to read the tool's output anyway, so why not? The only issue is, if you really want to, you can break the tool like that. Just say you have macros that expand to fold expressions depending on whether you're on a particular compiler or not. That's going to be really painful to detect, but again, that's something I have ideas for. That's not something I've been able to tackle quite yet, but hopefully in the future. Ultimately, what are your wishes? I'm really open to feedback at this stage, really interested in what do people want to see most, what are people concerned about most. That's kind of a good way to prioritize things as well right now. That said, you might have noticed I presented this tool first at CPPCon back in September, and originally it was designed as an open source tool because I just kind of hacked this thing together on a weekend, thinking, yay, let's just try this out, and then present it at CPPCon, and it'll probably never be stable enough to actually be used in production. And then I tried it out over the next couple of weeks, and I realized this thing actually works relatively well in practice. It's still going to be a massive amount of work, but I think it can be provide an actual benefit to your company when used in production even. So that's why I'm really looking to get customers for the tool. And that's where you come in. You're the developer community, so you benefit most from the tool, because you know C++17 is out there and provides a lot of useful features. But maybe you are in those shoes. You cannot actually use it, but you want to. So talk to your manager about it. Say there's this guy. It's not binding or anything, but you can always invite me for an on-site demo, and I'm happy to show the tool around and discuss how it might apply to your situation. But yeah, if you decide to go the way, you can tailor CFDF to your specific needs. You can tell me what language feature, what platforms will you compile the tool on. If you really badly need Visual Studio integration, well, that's what I'll be spending my next 2 weeks on. And if not, I can work on new language features. Maybe you're really excited about contracts. Maybe you're really excited about coroutines, for instance. All that kind of stuff. And maybe you just have some esoteric extra wishes, like you're working on an embedded platform with this particular vendor-specific compiler, and when you're doing this specific thing, you run into a compiler bug. That's certainly something CFDF could be extended to do, to automatically work around compiler bugs like that, so you don't have to. So just an idea, though. But yeah, it's a flexible licensing model. We can discuss whether we want a per developer license or a per line of code license, or whatever you find best anyway. But yeah, ultimately, let's talk, let's have a discussion. Not quite done yet, but thanks. I should have made that my ending slide, actually, but oh well. Use cases. This is kind of backwards, but if you're not quite sure yet, is this a tool for you? My main use case is basically early adoption of new language features. It kind of ties back into what I've been mentioning before. Think of all the code you're writing right now that will use outdated technology 5 years from, well, not 5 years from now, will be using outdated technology that technically was available at the time you wrote it. So you can just go ahead and, like, even if you're not familiar with the technology yet and need to bring your developers up to speed, you can have them experiment with CFDF. You don't need to, like, provide a test sandbox or anything. You can just install CFDF, have them use C++17 features right away. No need for any further setup. Maybe you're actually happy with what you got. Maybe you're using C++11 and you're just relatively content with the things it provides. Well, but there's certainly some growing number of C++17 or 14 specific libraries. Maybe you want to use those. Maybe you're really interested in regular expressions and want to use HANA's compile-time regular expression library. And you know, these things are usually into implementation details as well. Like the compile-time regular expression library has a C++11 interface, so there's no reason you couldn't use it other than the fact you can't compile it. So CFDF could enable you to compile it and use it in your otherwise C++11 code base. For example, ports to legacy platforms. Maybe you already have a working software stack that's running on a couple of platforms, but then a customer comes along and asks you, hey, I've got this really esoteric, really old platform. Can you port your software to that? And instead of saying, yeah, no, you can say, okay, yeah, we've got this tool. It can do it automatically for us. And ideally, it will just work. So that's an easy way to target to new platforms. And finally, maybe you don't care about all of that. Maybe you're happy with C++11. Maybe you don't care about all platforms. But there's this one feature or two features from the very far in the future standard, like contracts, like concepts, like coroutines, like modules. Well, modules is probably hard to achieve, but like these other ones. And you're really excited about those. Contracts, for instance, allows you to specify expectations you have for certain functions and standardize preconditions and post-conditions. It's a really powerful thing. And if you can use that standardized notation and just not care about any of the other transformations, that's something CFDF can do as well in theory. But yeah, that's about the main use cases I covered, but maybe you also have a fifth one. Happy to hear about that. To sum up, compile C++14 and 17 on an old compiler. That's the main purpose of the tool. It's a drop-in functionally. It's just a black box preprocessor for your current compiler. Has an easy integration into your existing build pipeline, assuming you're using one of the supported ones, but hopefully in the future also for less Unixy and less Makefile-based ones. And yeah, no source code changes needed in theory. There's lots of stuff to be done, but hopefully I get there in the future. But yeah. Right, if you want to have a look at the prototype code, you can go to GitHub. If you want to contact me, feel free to message me on Twitter, send me an email, check out my code on GitHub. Other than that, thanks for your attention, and maybe we have time for a couple of questions as well.
Thanks. First, I have a question. Do you already have some C++20 feature in mind that you think it's so cool that you want to implement it?
Certainly concept and contracts. especially because these are relatively, I don't want to say easy, but I've got very concrete ideas in mind about how I would tackle them. Especially because concepts specifically is largely a front-end feature, so it doesn't affect code generation or anything. It's mostly a matter of like which overload of this overload set do we pick, which compile error do we emit when one of the concept requirements isn't met, and similarly for contracts as well. It's just a matter of interpreting the post conditions and preconditions properly and inserting appropriate assert conditions in the function body instead.
Okay, and for the if const explorer, how do you know, or how does the tool know which types to specialize the template for? That's something that, I mean, if you had the is same with T and cat, and then the tool specialized it for cat, and which is okay, somewhat logical because it could figure out it's an is same, but then it also specialized it for the dog, and I don't see the connection. Like, what's the logic for selecting the types?
Oh, the logic is basically what the translation unit is using later out throughout the file.
Okay.
So if you look at the example, which one was it? 01B, I believe. Well, let's go with A. Everything's not more complicated than they need to be. So at the very bottom, I've got this function main that calls make sound once with a dog and once with a cat. So if I comment out the cat usage, for instance, oh, I'm in the wrong directory. So if I comment out the cat, it won't be using the well, it won't be using make sound with the cat argument anymore, so there's no reason to explicitly specialize for cat anymore.
Okay, thanks.
How do you prevent name clashing when you inject variables?
Sorry, come again?
How do you avoid conflict with the user code when you inject your own variables?
Oh, Clang allows for checking that. You can distinguish user-provided, explicitly generated, user-provided template specializations. You can distinguish those from the implicitly generated template specializations.
But for the types, but for the variables, when, for example, when you transpile structured bindings to other constructs, but you inject your own variables into the
maybe I should just fire up the structured binding example quick.
I'm not sure if it was structured bindings or one.
So does that affect this example?
Yes.
So I'm not sure I understand the question for you yet.
Temporary variable names you create.
What's that?
You create variables that those have names.
Mm-hmm, yeah.
I think he means name clashes with those.
Oh, right. Yeah, I don't think that's handled right now, but in theory you can just query the variable names used in that scope and just make sure that it doesn't clash. It's actually something I considered in, well, that's kind of why the CFDF binding group variable thing is so complicated. So users generally are unlikely to create a variable that is named equally. But yeah.
Thank you for your talk. I have a question about this template specialization. How do you tell libclang that you're interested in basically the AST after template after it initializes the templates?
Right.
So if you just walk the AST, that will just basically give you the structure of the source code, right?
I have a very good answer for that, actually. And Clang actually has a tool to directly dump the AST of a given source file. Use that using -x clang -ast dump, I believe. There's some way, I believe, yeah. Okay, there's some way to make the output, well, actually, that works. So the output is colored. So this is rather a lot. Let's see, yeah. So there's this node for the function template declaration. And you can see that Clang actually provides separate child nodes for that, for the actual function declaration that corresponds to the implicitly generated specialization here. So you've got one here, which I believe is the abstract template declaration, but this one is the concrete one for the dog. And well, I believe this is the one where I commented out cat, so there's no separate node. But yeah. Worth noting that the visit if statement function I showed before that handled this rewriting only operates on the implicitly generated specializations, or rather of the nodes thereof, because that's the only place where I know that. So that's something I have to take care of. So if I wanted to, if to run on the templated version of this thing, it wouldn't work, obviously, because at that point we can't statically decide which one is gone.
Okay, thank you.
Hi, so I have two questions. One, you had an example with a parameter pack, and after using your tool, you actually had the parameters TS1, TS2, and so on. Those names are generated by Clang, or you have a logic for generating those parameters?
Sorry, did you mean the fold expressions or the other one?
The fold expressions.
Okay.
Yes, I think so. Yeah, these ones.
Could you repeat the question again?
In the third example, after you use your tool, you have the function sum with parameter TS1, TS2, TS3, and so on. And my question is exactly this name, TS1, TS2, is generated by Clang, or you actually generate them like you have a logic for it?
That is handled by the tool, actually, because it was a massive pain to get Clang to like map the implicitly, like the expanded parameters and the implicit instantiation of the template. It was a massive pain to map those back to the actual abstract template parameter. So there's a lot of code in the tool that handles care of mapping, you know, what do those implicitly generated parameters correspond to in the abstract template. And yeah, making that kind of numbering scheme work was a huge pain, but it's handled by the CFDF.
Yeah, and the second question, so let's say the client uses GCC, but your tool actually uses Clang, right, to create the AST. So if the client software would not compile with Clang, then you wouldn't be able to generate this AST and modify it, right?
That's correct, yeah.
Okay, so he has to have it somehow compilable with Clang also before you use your tool.
I have some ideas. Maybe the tool can be made work anyway in those scenarios, because all you really need to be able to do is partially compile a certain file. And my hope is that maybe that will work, but it's not something I've really looked into quite yet.
And you think about like splitting per translation unit, or in a source file actually split parts of the source file?
Come again?
So you said you can split like which from where to get the AST, and my question was, you're thinking about to get the AST from only a translation unit and not from all, or you can actually think about possibilities to split the source file in different parts and get the AST only from different parts of the source file?
Yeah, the idea is basically as long as libclang is able to understand individual functions, I can still rewrite those. So say like in the extreme case, you have a translation unit with 5 functions in there, and the first one compiled just fine, but the last one makes trouble. I think in that case, libclang would still emit an AST for the first 4, but then stop at the last one. But I'm not entirely sure about that.
Okay,
but
thank you very much.
Thanks. There's one question in the back.
So what about error codes? Oh, error codes. So if your code produces an error, so does the CTFM produce a nice clang error? This is the line where it failed, and I don't know.
Not sure what kind of error you're talking about.
I mean, well, C++ 17 error that you would do, so forget the semicolon, or I don't know.
Right, we can try that out. Let's break our fold expressions example and just say, I don't know, just use 1, 2 periods right here. And try to compile it. I'm not specifying a front-end compiler because I don't need to. Tries to compile that, and it outputs the very same diagnostics you'd get from Clang in that case. So it just says expected expression, and yeah. Cool. There are no further questions. Thank you again for having me. It's been a pleasure.